1D kinematics with non-constant acceleration. So we finally get to how are you going to cope with it if you don't have a constant acceleration. Alright, it all comes back to these two base equations and their rearrangements. So there's the first pair and there is the second pair. Integral over dv, not integral over dv, integral of v dt, and integral over dx. And there's the second pair. So they're all related by derivative or integral. If you happen to be given the position, you can do dx dt and get the velocity, and you can do dv dt and get the acceleration. If you're given the acceleration, then you can do integral over acceleration dt and you can get the velocity, and you can then do velocity integrate over velocity dt and get your position. So you can go back and forth. If you're given the velocity, you can take the derivative and get the acceleration and then integrate it and get the position. So you can get equations for position, velocity, and acceleration from any of the givens. If you're given position as a function of time, acceleration as a function of time, or velocity as a function of time. And that's pretty much what you must do. I'm going to give you an example. I'm going to give you a quick problem where we have a non-constant, a very obviously non-constant, acceleration. We're going to say that it is some base value of acceleration times cosine of 2 pi over the period times the time. Okay, the period is just telling us how long it would be before the acceleration completes a full cycle and comes back to where it initially started, at positive a. This is very clearly not a constant acceleration. If we plot this thing, it's doing the very typical cosine thing. So we actually have our period in here. I'm not going to give numbers for this, but we're going to take this and we're going to figure out what is the velocity at any future time, what is the position at any future time, given one extra piece of additional information, which if you're having to integrate, you do need a little bit of extra information. And in this specific example, we're going to say v and x are 0 at t equals 0. In other words, it begins at 0, it begins at the origin, and it begins at rest. Begins at origin, at rest, at t equals 0. Okay, so what we will have to do, if we want to know the future velocities of this, we'll have to take our a dt and integrate, and we'll have to take dv and integrate it. What that's going to look like: integral from 0 to some future time of our equation a cosine 2 pi over the period times the time d time, integral from v initial, which is 0 in this case, to whatever our final velocity is, dd. Alright, you do have to use a quick u substitution here. So u is equal to 2 pi over period times time. Take the derivative, you get the 2 pi over period. You'll have to divide by that. So we're going to get a times t over 2 pi. The integral of cosine is sine. And 2 pi over t, that. We do have to think about what happens with our limits here. So I'm going to leave it like that for the moment. On the other side, we just get v. Let's complete this step. So what is sine of 0? It's 0, so the 0 term will go away. That is not always the case, so be careful. Matter of fact, we'll get an example of that in the very next part. Okay, now we want to get position. So we'll have to do an integral of v with respect to time and integrate our position. Okay, the limits on this will be from 0 to some future time, and from 0, because we start at the origin, to our final position. So we're going to get this side integrates to just x. Then we'll have integral from 0 to t of our constant a times period over 2 pi sine of 2 pi over the period times time dt. All right, quick u substitution again. We'll pick up another t over 2 pi. So a t squared over 4 pi squared. Integral of sine. Well, derivative of sine is cosine, derivative of cosine is minus sine, and you get the opposites when you're going backwards. So integrating cosine gives sine, but integrating sine gives minus cosine. And it'll be minus cosine of 2 pi over t times the time, and we'll have to evaluate between 0 and t. All right. So a period squared over 4 pi squared. Then we get minus cosine 2 pi over t times the time for the upper limit. For the lower limit, we subtract a minus cosine of 0. Cosine of 0 is 1, so we've got a minus minus 1, so we've got, it kind of inverts the order here. We've got a plus 1 and we've got a minus cosine. So it'll be 1 minus cosine 2 pi period, 2 pi over the period times the time. Now we should check. This should give 0 at t equals 0. And quickly throwing in 0 for t, it does. So logically it worked out. There's our answer for future positions. There is our answer for future velocities. It's really a fairly straightforward process. You just have to recognize you are in a condition where the acceleration is not constant, and you run from there. All right, there are a couple more examples posted or in the practice, so make sure you take a look at them. All right, that's it for this one. See you in the next one.